We're going to go over our practice for condensation reactions here. Part A, we can see based on the ester as well as the sodium methoxide that we're dealing with what is most likely a Claisen condensation. That means our nucleophile is going to be our ketone, and at its alpha carbon, it's going to do an alpha substitution with the ester. Part B, we also have a Claisen type reaction. This one is going to be intramolecular and will yield us a six-membered ring. Now we did have a choice of two carbonyls here. And when I did this one, when I gave the solution, we went with this carbon as our enolate and therefore our nucleophile. Why did we go in that direction? Well, the base here is a relatively strong base, sodium methoxide. So we're making the assumption that it's going to be irreversible, and we're going to form the less substituted or the kinetic enolate. Part C is an aldol condensation. We can see that benzaldehyde on the left has no alpha carbons. It's not going to be able to serve as our nucleophile, whereas cyclopentanone does have alpha hydrogens. This is going to form our enolate. And that's going to add in to the benzaldehyde to give us the corresponding aldol condensation. Part D, we have a 1,4 carbonyl. That's our Michael acceptor. Recall that with condensation reactions, just like many other 1,2 versus 1,4 additions, enolates are sufficiently good nucleophiles that if possible, they will leave and give us the more stable 1,4 addition. Part E, a bit more complicated. We're going to start by forming the kinetic enolate, and that's because we've got LDA, which is generally a strong irreversible base. That enolate that forms, we'll do a 1,4 addition into the carbonyl of the other compound. Then if we reverse to the other enolate, remember this is always going to be in equilibrium. So if we no longer have that carbonyl, that enolate, but instead have that one, we can get an intramolecular aldol. Why does this occur? Well, because this is perfectly set up to give us our most stable ring size, six-membered ring. Once that six-membered ring forms, we can protonate and finish our elimination. And as a result, we We end up with our aldol product and we complete our Robinson annulation. Now, all that being said, if you want to see a little bit better where that ring is coming from, we're going to go through that. So I'm going to grab this whole structure. And we're going to bring that down here. And now what I'm going to do, we're going to erase this negative charge in the arrow because that becomes a double bond. These pi electrons go away. And they form a new bond to that carbon. And then those electrons shift up onto oxygen. Now, that doesn't show us the six-membered ring very well. If we look carefully, we can see the 6 carbons of the ring. But now we're going to redraw them. And we'll number them again. And then we can transfer the substituents on each carbon over to this newly drawn structure. So carbon 1 has a methyl, 2 has a carbonyl, 3 has nothing, 4 has a propyl group, 5 has nothing, and 6 has both the O- and an ethyl. Now you can see it's not exactly what I have drawn over here. You would need to rotate it 180 degrees that way, but it is the same structure. And in order to finish the reaction, all you need to do is protonate the oxygen and go forward with the elimination. So now let me erase some of this so that I have room to work on part F. Part F is a much more straightforward reaction. It's another example of a Michael addition. Again, strong irreversible base gives us our product. All right, question 2. We have a mechanism question. And some of you might look at this one and say that ketone that's there probably not going to react. It's too starkly hindered. And that's certainly feasible. But let's just assume that it is able to react. So the reaction here, we have another aldol. This is a mixed aldol, but only our ketone on the left can form an enolate. So base comes in, removes the hydrogen, and we form an enolate. That enolate would then attack the other carbonyl. And we're just going to abbreviate the groups to make this easier to draw. The oxygen gets protonated. And from here, it's just a matter of carrying out the elimination. So base grabs this, we form another enolate. And that enolate will kick out our leaving group. All right, so finally we have a couple of synthesis questions. This first one probably looks fairly complex, but as we'll see, um, not nearly as bad as it looks. So we know that there is a carbonyl there, and if I assume that at some point I'm going to get rid of that carbonyl, maybe in the last step I'll do a Wolff-Kishner. That will get us to there. And then presumably we could add in all of those carbons there by doing an alpha substitution. In this case, it would be double alpha substitution, but it would allow us to get there. Now the complication comes in that we need to get 2 additional carbons on there. We need to do an elimination, but we also need to end up with an unconjugated alkene. Now, if I took my original starting material and added base plus an ester, that could give us this dicarbonyl. Now, how am I going to get from this dicarbonyl the rest of the way there? Well, if I reduce it, only problem is if I try to reduce that carbonyl, I'm going to reduce both of them. So I need to be able to do this in a way that's only going to reduce one of my 2 carbonyls. And given how similar they are in reactivity, not all that likely. So is there anything else I can do instead? Well, what this may mean is that I need to back up a little bit. So let's go back to the beginning. And think about what we might add to this carbonyl that's going to let us do what we need. So what if instead I'm going to use all of these steps that I have, but I'm going to change the order. So what we tried originally didn't work. But I'm going to again do this Claisen condensation to get the dicarbonyl. Now, this dicarbonyl, again, I'm going to do an alpha substitution, in fact, the same double alpha substitution we had previously. To give us our 6-membered ring. Now, something interesting is going to happen. If I do a reduction with sodium borohydride, it's going to reduce both carbonyls. I have no way to avoid that. They're both ketones. They're going to have similar reactivity. But now let's do an elimination. So acid and heat. If I do that, the alcohol on the left can't eliminate. Why not? There's no hydrogens here. So it can't eliminate, but the one on the right can. The one on the right also can't give us the more substitute alkene, because again, no hydrogens on that center carbon. What do I need to do from here? So now I'm going to reoxidize that alcohol. I can do that using PCC. And finally, a Wolff-Kishner will allow us to eliminate to get, remove the oxygen. So a little more complicated, but a good illustration that in synthesis, the order that you put the steps in really makes a difference sometimes. All right, finally, our last of this group. Another synthesis. And the key here is we really need to get all of these extra carbons on. Well, the easiest way I know to do that is with an aldol. And as we'll see in a moment, that aldol is not only useful because it gets me all of the carbons I need, but notice I need to get 2 more oxygens installed. And the aldol I just used leaves me an alkene here, which upon dihydroxylation with osmium tetroxide and NMO, I get the diol, and then PCC will be good to oxidize both of those up to the carbonyls.